So, good afternoon, everybody. Welcome to another Heidelberg Joint Astronomical Colloquium. And this week we're moving right out into the far reaches of the universe, something we've been anticipating all term. And we have Roberto Maiolino from the University of Cambridge and the Kavli Institute for Cosmology in Cambridge to tell us about the particular new results from JWST. And his host, Dylan Nelson, will provide the full introduction.
It's my pleasure to welcome Roberto Maiolino, a professor of astrophysics at the Department of Physics and the Kavli Institute for Cosmology, University of Cambridge, honorary professor at University College London, and member of the Royal Society. Has just been awarded recently his second ERC Advanced Grant. Congratulations on the topic of the emergence of the first galaxies and supermassive black holes in the universe and their subsequent evolution through cosmic time, which is what he will tell us about today. It's a pleasure to have you here. The stage is yours.
Thank you, Dylan. Thank you, everyone, for coming. It's the first time I'm back to Heidelberg since before the pandemic, so I'm really glad. So I will be presenting some of the first results obtained through the GTO program of the NIRSPec instrument on JWST. And of course, this is on behalf of a much larger collaboration, particularly, of course, the NIRSPec team. And as you will see, actually involving also other collaborators from other teams. Just to mention that I have been in the NIRSPec team nearly for 20 years, so it's been taking this large fraction of my career. And this is the first version of the team, and you can recognize some people, including Hans Walter, who is, of course, couldn't be here, I understand, today, but we have been in this adventure since the very beginning. And of course, now the team has evolved a lot with many more people. This is just a fraction of them. Towards the end of the pandemic. And as I mentioned, actually, we have been, a large fraction of the program has been undertaken in collaboration also with the NIRCam and the MIRI instrument teams. Then this is one recent collaboration meeting in Tucson. So there's been a lot of anticipation about Webb and for a reason, as you see, in some spectral bands, the increase in sensitivity with respect to previous facilities is more than 3 orders of magnitude. Now, such a huge leap in sensitivity has happened really rarely in astronomy, but even more broadly in science. So, you can, to put it into a context, it's equivalent to suddenly indivisible passing from Galileo's telescope to modern large telescope. So you can think of something like 400 years of discoveries, possibly compressed in a few years of operation of JWST. So we are all, of course, extremely excited about this. You have certainly seen some of the first fantastic images from Webb, and here in Heidelberg there is also a major involved in various programs, and some of these images of nearby galaxies have been produced actually here in Heidelberg. I won't be focusing much on these fantastic images of nearby galaxies, but I will mostly focus on the high redshift universe in the distant galaxies, which is where we are essentially investing most of our guaranteed time. So the goal is, of course, to explore how stars formed across cosmic times. And we know that they have peaked around redshift 2 about 10 billion years ago. And how during this period the galaxies have assembled and built up their stellar mass, and in doing so, how they have enriched their ISM and the stellar population of chemical elements. And of course, the goal is to push as towards the cosmic dawn, the first epoch of formation of galaxies, and most of the observing programs in cycle 1, so during the first year of operation of Webb, have been focused on going beyond cosmic noon, as I said, towards the earliest epochs, and how high in redshift, of course, will depend on how collaborative the universe is and how generous the universe is. And as I will show, it seems that actually, indeed, the universe seems to be quite generous in terms of discoveries and new population of galaxies at a high redshift. So, of course, Webb is optimized for the infrared, and in this context of the studying the formation of galaxies, it's the motivation is that, as we know, the cosmic cosmological redshift pushes most of the spectral features and diagnostics in the infrared, and of course the galaxies becomes also gradually redder and redder because the intergalactic medium absorbs the light shortwards of the Lyman edge and then shortwards of Lyman alpha. So that's the key important aspect of Webb being, in this context, optimized for the infrared. And you have all seen the first images with this fantastic population of galaxies, in this case in the background of these lensing clusters, which are distant galaxies up to the galaxies which are seen as they were in the first billion of age of the universe. Oh, let's start to dwell in some of the early results, which have been coming not only from our collaboration, but actually from many other programs. In particular, there have been a set of programs which were designed actually to provide early results in the lifetime of the observatory, and also for the community. One of the first results, in this case from the so-called CIRS survey, which has been mapping a distant region of the sky in various filters with Webb, has been that there are quite maybe too many galaxies with luminous in the early universe, more than what was actually expected. So what you see here is a sort of luminosity function, so a surface density of galaxies in the ultraviolet rest frame at beyond a certain redshift. And this is the shaded regions indicates the observatory distribution of galaxies, a function of redshifts, and all of these are different models. And you see that most of them were not predicting that many luminous galaxies at such high redshifts. So these have been triggering speculations that what's going on, maybe there is a top-heavy EMF which makes these galaxies more luminous in the ultraviolet. The other, initially at least, puzzling results was the finding of extremely massive galaxies again in the early universe. And to the point that some people, and actually this has been done by various groups, have been questioning, discussing whether this actually was consistent with the widely accepted standard models, lambda CDN model of the universe. And what you see here, you see these distributions are indicating the maximum stellar light that you expect in galaxies as a function of redshift according to these cosmological models. And you see that these observed galaxies, which are these points here, are actually in excess of these, even the 3 sigma predictions. And even in the most extreme case where you actually convert all of the baryons into stars at these early epochs, which is, we know, is certainly not the case, because in the local universe, only a small fraction of baryons are stars. So at that time, there is still a long way before actually converting a decent fraction of baryons into stars. So it seems that these early results were somehow in strong tensions with what was our understanding of the early universe. However, keep in mind that many of these results, which one of the issues is that most of these redshifts, that is the cosmological distances estimated for these galaxies, are based on the photometric information, that is images in multiple bands. And the photometric redshift techniques consist in the fact that as the galaxy, you observe galaxies at higher and higher redshifts, what happens is that the sharp drop of light due to the intergalactic medium absorption at short waves of Lyman edge and Lyman alpha goes past through redder and redder filters, and so you start seeing the image of the galaxy fading in bluer filters. And by combination of filters, you can somehow infer the redshift and therefore the distance of these galaxies. However, to get a proper redshift, you need actually a spectroscopy. Why? Because you can be fooled sometimes, and the main culprit of this fooling photometry are primarily the potentially strong emission lines, nebular lines in the spectrum of these galaxies. And this is shown quite clearly in this example. So this is one of these galaxies which have been proposed, identified to be, suggested to be at redshift of 16, based on the fact that you see in the shorter bands, in the bluer bands, the galaxy is not detected, while it's fairly strong in the red bands, okay? However, the same kind of photometry, so the light in different bands, can be fitted and reproduced equally well by actually an intermediate redshift galaxy at redshift about 4.6, with a template in which you have a galaxy at lower redshift with strong nebular emission lines. Okay, so there is this risk of the so-called photometric redshift being fooled by emission lines. Of course, you need really strong nebular lines to affect these images in the broadband photometry. So we have to see whether that's really the case. The other problem is that the same nebular lines can fool also the estimation of stellar mass. And you see this in this example again. This is again a galaxy with strong emission in the red bands and essentially totally invisible in the blue bands. And initially this was interpreted as a galaxy at redshift 7 with this strong continuum emission in the red bands, which is indicative of a very high mass. So this is one of these very massive galaxies that potentially can, whose large number can be problematic to interpret with the current models, okay? However, again, the same photometry you can fit again with a much less massive galaxy, okay, at slightly lower redshifts, where the bulk of this red emission is dominated by strong nebular lines. So we have to check again spectroscopically whether that's the case or not, because as you see, there are big implications at stake, so that we can have to revise entirely some models or not. So, and this is one of our several goals of our program of the GTO program of the NIRSPec instruments. We have essentially several hundred hours dedicated to obtain a survey, spectroscopic surveys of a large number of galaxies, and we use primarily two modes. So one is a multi-object program, where we use this so-called multi-object mode, MSA, multi-object mode of NIRSPec, where you can take simultaneously spectra of about 200 galaxies simultaneously. And in this case, we have dedicated to this kind of survey nearly 900 hours to obtain spectra for about 10,000 galaxies. And this is the number of targets as a function of depth that we are aiming to obtain at the end of the survey in this survey. As you see, there is a multi-tier survey. And we are using most of the dispersers available on NIRSPec, so low resolution prism for stellar population, medium resolution for the characterization of the interstellar medium, and also high resolution for the detailed kinematics. And we also have an integral field program, which is essentially targeting individual objects where you can obtain three-dimensional spectroscopy, so both spatial information and spectroscopic information, and this is limited for about 40 galaxies in this relative range, which are observed in depth. And I will show examples of both surveys. Again, everything is just started, so we have several results, and I will focus on a few examples of these results, but I don't have time to explain, to show all, and also keep in mind that it's everything in evolution, so we are actually updating these results as we speak. As I mentioned, the NIRSPec GTO program is not done in isolation, especially for what concerns the multi-object mode. This is done also in coordination with the NIRCam team, which is the primary imager of the observatory in the near infrared, and MIRI, the MIRI team, which is the imager and spectrograph in the mid-infrared band. And it's a complex survey where we use one instrument, NIRSPec, to obtain spectra while obtaining images with NIRCam or MIRI in the other in parallel, and then we swap to obtain spectra of the galaxies that were observed with NIRCam and obtain other images with the other fields with NIRCam and MIRI. So it's a very complex survey strategy. As you can see, this is an example in the so-called good south, which is a very deep field in the southern hemisphere. But we have a similar design in other areas, in Goods North and other shallower areas. So this is a first image of the mosaic obtained with NIRCam with the first few pointings in the good south. And so in this area, each of these little dots is essentially a distant galaxy. We essentially are detecting about 100,000 of them. And this is an image done, well, we have this image in essentially 9 to 14 different filters, okay, with down to very deep depth. We are still acquiring data. Unfortunately, only a fraction of the time that it should be allocated has been executed and will be executed in the coming months, and a fraction of these will be actually completed in cycle 2. Of course, you can't appreciate the quality of the data based on this large-scale mosaic. I can only illustrate some representative example. You find galaxies weird as this one, which is a chain of I don't know, interacting galaxies. The same here, but you also see very how to say regular disks at high redshift with knots of star formation. And of course, you want to appreciate the huge improvement with respect to the Hubble, which is the predecessor essentially of Webb, and mostly in the optical. And you see that with Webb you can in these distant galaxies clearly resolve the spiral structure of these systems, the individual star forming regions along the spiral arms. Okay, these are just to illustrate some examples, but what I want to just dive immediately is the main objective that we have. One of these being, of course, exploring the redshift frontier. So again, exploiting both the infrared optimization and the sensitivity of Webb to find the most distant galaxies and close to their epoch of formation. And these were some of these initial galaxies that we found, that essentially are these tiny red dots, which appear red because indeed the bluer bands are completely essentially absorbed by the intergalactic medium. And of course, these were initially the photometric redshifts of the galaxies, and which were confirmed by subsequent spectroscopy with NIRSPec. And this is the image from the press release that we used when we published issued this result. But I think it doesn't make justice to the quality of the spectra, and I think this is, which is from the paper, shows better how we are identifying the redshift. Primarily, essentially, the redshift, you are seeing primarily the stellar continuum, and you see this clear, strong break shortwards of a certain wavelength, which is an unambiguous identification of the redshift due to the fact that and shortward of Lyman alpha at this high redshift, the whole flux, stellar flux, is absorbed by the intervening intergalactic medium. And okay, these are just, and you see this clearly also in the 2D spectrum, which is leaves no doubt that this break is clear. So we can now we can now say that these are genuinely galaxies that redshift higher than 10. So when the universe was about between 300 and 400 million years old. So it's actually an eye blink with respect to the overall life of the universe, which is more than 13 billion years. Okay, what do we infer for these early galaxies? These are simply results from reproducing the observed photometric, broadband photometric information. And so these are fairly low mass galaxies, what in the local universe we would call dwarf galaxies, okay, with masses below about 10 to the 9 solar masses. So we don't find, for the moment, at this high redshift, any evidence for these hypermassive galaxies. Fairly low star formation rate, but about 1 solar masses per year, which may sound low, but actually are actually fairly high for this kind of low mass, because 1 solar masses per year is about the star formation rate of our own Milky Way, which is about 2 to 3 orders of magnitude more massive than this system. So in terms of star formation rate per unit mass, these systems are much more powerful by 2 to 3 orders of magnitude, okay? And of course, these tend to be very young systems. Not surprising. We are seeing this system just as they have formed in the early universe, with ages of about a few tens million years. If you include also the information from spectroscopy, you get additional information, which I don't have time to go through in detail, but I think an interesting aspect is that these are relatively low metallicity system, typically with metallicity of 1/100th of solar. And interestingly, there is also some indication of some dust absorption, and I don't have time, unfortunately, to discuss our results on the dust, but I can discuss with you maybe a question time or during beer later on in the evening. Okay, so these are for the most distant galaxies that we have identified, and the most prominent nebular lines in this case, which are typically in the optical, are redshifted outside the band observable with the NIRSPec. But as you go to slightly lower redshifts, you start to see these fantastic, spectacular emission lines, which are in the optical rest frame and redshifted to the near infrared at this redshift. You see these strong oxygen-3 lines of oxygen ionized twice, which in our use this kind of notification. The Balmer lines, H alpha, H beta, and various other emission lines. So these are actually quite very strong nebular emission lines, which are so strong that indeed they can seriously affect the broadband photometry in the infrared. So they can actually cause the kind of issues that we have discussed a few minutes ago, so affecting both the photometric redshifts and the stellar masses. So the question is that this kind of very strong lines you very rarely see in the local universe. So what is why you see so often these kind of strong emission lines at such high redshifts? What is responsible for these very strong, extremely strong nebulous lines? So this comes from the interstellar medium ionized primarily, we think, by the strong radiation field of young stars which have just formed. And on this diagram, you see the ratio between oxygen, this line powered doubly ionized oxygen to singly ionized oxygen on the y-axis. And on this axis, you see the ratio between the sum of these lines to H beta, okay? And you see this is the distribution on this diagram of local galaxies. And these purple and red points are our galaxies at redshift around 6 to 8, okay? And you see that the characteristics of these high redshift galaxies is that they have much higher ionization stage than local galaxies, with the oxygen, double ionized oxygen, much stronger than the oxygen 2. So, and this is this line ratio is a proxy of the so-called ionization parameter, that is a measure of the density of ionizing photon relative to the density of the gas, which means that these galaxies are producing a radiation field from young hot stars much stronger than local galaxies. And there is also an effect of metallicity. Lower metallicity tend to result in harder radiation fields from the young stars. And yes, it works. And this is for the galaxy for which we could measure the metallicity, the distribution of their metallicities. So solar is about here, okay? And you see that in local galaxies, galaxies at redshifts that we explore with NIRSPec from 3 to 10 have typically lower metallicity, of course, than the local universe. But there is a lot of scatter. In particular, you see that what you see here is the metallicity as a function of stellar mass, and this is the so-called mass metallicity relation for in the local universe, so that the metallicity scales with stellar mass, and this is what is obtained at redshift 2 and redshift 3 from previous surveys. We are mostly exploring the very low mass regime. For the moment, we have more galaxies coming in this range here, and you see that these high-redshift galaxies tend to, how to say, stay on the extrapolation of the lower redshift mass metallicity relation, but and the inclination is that with the higher redshift you tend to have lower metallicities, but the bottom line, I think, is that there is a huge scatter, which means that these galaxies are in the process actually of strong and stochastic evolution, and partly where you actually they form stars, they form chemical elements, they expel chemical elements through galactic outflows, and they accrete new gas which dilute their metallicity. So you have probably a lot of this is probably partly responsible for this large scatter. Another important aspect, however, is that for a number of these galaxies, which we are trying to quantify for how many, we see evidence for the Balmer lines of hydrogen and some other permitted lines of helium, of these broad component, you see, which is not present in the other metal lines, which are so-called forbidden lines. And this is a clear signature, unambiguous, of gas in the process of accreting a supermassive black hole. And so it's affected by the strong gravitational potential of the supermassive black holes responsible for this large Doppler shifting. And essentially is therefore an ambiguous signature of black hole accretion, which we call active galactic nuclei. And from the width of these lines, we can also infer the mass of the black holes, okay? Which is, in this case, something like 3 times 10 to the 7 solar masses, which is actually fairly small for these high redshifts, because so far previous surveys have mostly focused on looking for a much brighter system, much brighter agents, which the so-called quasars, which have typically much significantly larger masses. This is another of these examples, which has a much higher signal to noise. This was targeted with the integral field unit, and was not targeted because it was a known AGN. It just happened to be to turn out to be an AGN. And the spectrum is spectacular. Essentially, you don't see the noise here. Each of these blip is actually an emission lines. And this is led by Hannah Hubler and a postdoc in Cambridge. And I asked Hannah, can't you find a way to show somehow the noise? And the only way she found to do this is to plot the y-axis in logarithmic scale. In that case, you start to see some of these people noise, but here we're talking about 1, 2, 3 orders of magnitude in dynamic range between the emission lines and the noise, okay? An interesting thing you start to see these broad components again of the Balmer and the helium lines, which are in the, again, unambiguous tracers of accretion of gas surrounding a supermassive black hole. And you actually see many other transitions. Argon 4 is a really beautiful spectrum. It's sort of a kind of spectrum that you often you don't get even in the local universe. So it's fantastic to see these things at the redshift 5, nearly 6, with this quality. And again, from this broad component, you can estimate again the black hole mass, which in this case is closer to the 10 to the 8. And you can compare these black hole masses with the mass of the host galaxies. And in local universe, we know that the black hole mass somehow correlates with the mass of at least the spheroidal component of the host galaxy. And this is the relation that we see observed locally. And there's been already in the past, and the people here in Heidelberg has been working a lot of these, indication that for quasars at high redshifts, there is a tendency for the supermassive black holes to be overmassive with respect to their host galaxies. And this was somehow suggested to be indication of a bias to the fact that at high redshift we tend to select preferentially more luminous quasars, which tend to be associated with more massive black holes. But actually, we see that in these systems that we are detecting now at a much lower, luminosities, and therefore much lower black hole masses, these still are above these relations. So they have black hole masses which are overmassive with respect to their host galaxy by an order of magnitude with respect to the local relation. And this is highly relevant for understanding the formation of these monsters. Indeed, you know that essentially we think that essentially any galaxy has one of these supermassive black holes at the centers. There's been a lot of press releases in the last few years, for instance, with the direct imaging of the black hole in our own Milky Way and in M87. But the key point is that this kind of monsters black holes with masses of billions solar masses had been found already to be already in place at redshift around 6 or 7, so when the universe was less than 1 billion years old, and explaining such huge masses of black holes so early in the universe has been challenging for theories because there is not enough time to grow these hypermassive black holes. So there have been various theories which have been suggested, so that supermassive seeds resulting from the direct collapse of massive clouds, nuclear runaway over nuclear star clusters which merge in the center of galaxies, as well as pop-3 remnants. So the finding of these hypermassive, so these black holes already in place with these high masses and being overmassive with respect to their host galaxies tend to indicate that probably these already evolved from direct collapse black holes, but still we have to find more examples at even lower masses in these surveys. The other interesting aspect is that we tend, in most cases, we do not see these broad components of the hydrogen lines or helium line. We rely on finding these accreting black holes through some diagnostic diagrams of other nebular lines, which are more easy to detect. In particular, the ratio between, again, these double ionized oxygen lines to H beta and the single ionized nitrogen to H alpha, okay? And in this diagram, typically star-forming galaxies are in this low ionization region, and while AGNs are in this region here. Now, for these AGNs that we detect at unambiguously identified through the broad component at these high redshifts, their narrow component actually do not fall in this region of the AGNs. They are actually shifted in the region of star-forming galaxies, which means that it's actually very hard now to identify these high redshift AGNs because they cannot be, spotted through the traditional diagnostics that we were used to use in the local universe at the lower redshifts. And you may ask why they are located here. Well, one possibility is that they're, despite hosting AGNs, their nebular line emission is outshone by their host galaxies. But one possibility is that we are hitting the era when actually we are starting to see accreting black holes in relatively low mass galaxies. And in that case, you expect that the characteristics nebular emission of active nuclei essentially move towards this region. And this is illustrated by these photoionization models, which I developed together with Kimiko Nakajima, where from red to blue, essentially you move from supersolar to very subsolar metallicities, and essentially these high redshift AGNs occupy the location indeed of AGNs in low metallicity systems. Now, another question about these AGNs is whether their strong radiation field drive galactic outflows. And this is actually an important question because galactic outflows are thought to be a key aspect of regulating galaxy evolution. And we do actually see outflows quite often, and typically AGN-driven at these high redshifts. This is a case of a quasar at redshift 6.2 observed in our survey, which has, so this is a spectrum which is continuously attracted, so again shows this spectacular strong Balmer lines and this oxygen tree line. And this is a map in oxygen tree, okay, this double ionized oxygen. It shows a clear companion. So we see companions very often, okay, nearly essentially, currently any AGN has a companion galaxy. But the host of the quasar is this one, okay? And when you look at the kinematics of this oxygen tree line, we see that it has actually a very peculiar velocity with very high widths, which is a sort of essentially an ambiguous evidence of a prominent outflow, which is essentially being driven by the radiation pressure of this quasar. And we see this essentially in any of these AGNs. Now, it doesn't, if you compare with the lower redshift AGNs, they don't seem particularly different, okay? This is an illustration of the outflow rate in these AGNs as a function of the luminosity of the AGN. And the blue points are local and low redshift galaxies, and these stars are some of these AGNs that for which we could map the outflow, and they essentially follow the same relation as local and low redshift galaxies. This is the kinetic power as a function of AGN luminosity, and essentially gives an indication of how effective is the overall system. So the coupling of the radiation of the and the energy injected by the AGN in coupling with the ISM in driving these galactic outflows. And again, typically this region is thought to be not particularly effective in expelling gas from the host galaxy. And we see that these high redshift quasars seems to be essentially located in a similar region as lower redshift AGNs, so with relatively mild outflows. This doesn't mean that these outflows are not actually important for the evolution of the systems, because first, we are only probing here a single phase of these outflows, a warm ionized gas, while there are other phases which can be more massive and more energetic. And the other thing is that this is essentially the alpha, which is essentially coupled with the interstellar medium of the galaxy. But actually, a large fraction of this outflow can escape into the circumgalactic medium, heat the circumgalactic medium, and actually have an indirect effect on the evolution of their host galaxies by essentially preventing accretion of new cold gas onto the galaxy. And all of these is highly relevant for what we call the local galaxy bimodality. As you know, broadly speaking, local galaxies are divided in star-forming, gas-rich, and with young stellar population, and passive, quiescent with the little gas and older stellar population. So one of the challenges of modern astrophysics is to understand why and how these star-forming population at some point stop forming stars and become passive and quiescent. So you need some mechanisms which stop the star formation. And if you want to explain also the different morphology and dynamics in these systems, you also have to invoke some sort of morphological and dynamical transformation. Now, there have been various possible mechanisms and causes. I have summarized these in this chart, and I'm sure that Annalise and Ellen will be horrified by this simplified cartoon, but essentially gives you some of the main scenarios that have been proposed. That is removal of gas, which essentially implies that you remove the fuel for star formation, or reducing the efficiency of star formation, or essentially preventing the accretion of fresh gas and therefore resulting in quenching star formation by starvation. And there have been, there could be various culprits responsible for triggering any of these mechanisms. One could be the environment in which galaxies live, supernova explosions associated with starbursts, AGN activity, that is backdoor accretion, and other effects associated with the instabilities and gravitational shocks. Let's say that each of these can contribute, but there is a sort of convergence, if I'm allowed. Again, some people may scream that I'm oversimplifying the whole thing, but let's say that generally we think that, well, at least a number of people think that, at least for low mass satellites, the environment is the primary mechanism responsible for halting star formation, while for massive galaxies, black hole accretion, either in the form of ejection of gas or heating the circumgalactic medium and preventing fresh accretion can be the primary mechanism responsible for stopping star formation. I must say that there's been several papers claiming that this quenching of star formation must be accompanied by morphological and dynamical transformation. That is, the merging of galaxies results in boosting the star formation and the black hole accretion, which essentially expel the gas and result then into an early type galaxy, in elliptical galaxies, so quenched, and therefore explaining both the quenching and the morphological transformation with the same process, okay? Now, we have obtained some interesting results in the last few minutes that can shed light on these various mechanisms, because at this point, since these systems are fairly old, and means they quenched at higher redshift, we can explore these mechanisms directly by finding these quenching and quenched galaxies in the early universe. And these, I promise this is the last few minutes. This is one of the first example, which is quite impressive, because this is a massive passive galaxy, so 10 to the 11.4, so quite massive at redshift 3, which is already completely quenched. It's not forming stars. And for this, we have obtained high resolution integral field spectroscopy, that high resolution both spatially and spectrally. And the signal is so high that we can actually detect the individual absorption stellar feature. And doing so, we can actually map the kinematics of this galaxy. And what we find, so we can obtain the stellar velocity field of this passive system. And what we find is that there is a passive galaxy in the early universe is actually rotating. So this is what in the local universe is called a fast rotator, but at redshift 3. This means that this essentially was a disk, okay, which has quenched without any dynamical harassment, without any merging, but with a gentle quenching, simply by removing it or by starvation, okay? Any morphological and dynamical transformation, which later on may have transformed this into an elliptical galaxy with a lot of dispersion and without rotation, must have happened later on. The other interesting fact is that you see these nebula lines. These are not tracing star formation. These are tracing again an AGN in the host galaxy. And the other interesting thing is that you see there it has this satellite galaxy at the same redshift, which is much less massive, and this galaxy too hosts an AGN. Okay, so it seems in this case we have a double AGN associated with this quenched galaxy. So and you will see, keep seeing these AGNs commonly present in these passive systems, star redshift. So the AGN probably may have caused the galaxy to stop our formation, and is also probably responsible for keeping them quenched, okay? And the interesting thing is that these satellites will certainly merge with the more massive galaxies, and therefore start with this process of dynamical and morphological transformation, okay? Now, when this galaxy star formation quenching start? Now you may have seen yesterday appearing on archive on our AstroPH this paper by Adam Karnal, this fantastic galaxy at redshift 4.6, fairly massive, quite massive, which is already quenched, confirmed spectroscopically at these high redshifts. And also, in this case, there is this evidence of strong AGN, again, associated with this already quenched galaxy, okay? So this was, until yesterday, the most distant passive galaxy spectroscopically confirmed. Interestingly, in our survey, we have actually discovered the quenched galaxies at even higher redshift. So this, in this case, is actually a low-mass galaxy, essentially a dwarf, which is as a spectrum of a totally quenched galaxy. We don't even see any hint of a nebula lines hinting for any star formation. So this galaxy doesn't have star formation at all, okay, as far as we can detect in terms of sensitivity of the spectrum. And here, this is at redshift 7.4. So we are in the reionization epoch, okay, the epoch of formation of the first galaxies. And this guy has already undergone a quenching event. The signal to noise is high enough that we can extract the star formation history of the system. And essentially what we get that, and by using different codes, they give the same results, essentially, that this galaxy has gone through a short burst of star formation and followed with a very rapid quenching of star formation. And essentially the galaxy has been quenched for about 20 mega years. And the stellar metallicity is very low, less than 100 times lower than solar, meaning that the quenching has been so fast in these early times that the supernovae didn't have time to enrich the ISM out of which the next generation of stars formed, okay? So it's been a very rapid phenomenon, okay? So what quenched these low mass galaxies so early in the universe is not clear, honestly. What I can say, we have tried to compare with some expectation from some cosmological simulations. I was discussing this earlier this afternoon, this morning with Annalisa. But for the moment, the only simulation that I could see predicting quiescent galaxies all the way to very high redshift in the reionization epochs is this simulation combination of the so-called Eagle simulation and essentially a revision, a combination with the additional techniques. Let's say I don't have time to expand on that. And they don't have the resolution to explore very low mass, the very low mass regime that we are that we are detecting. The lowest mass that they are sensitive is 10 to the 9. But this essentially is giving you the number of quiescent galaxies as a function of redshift. And as you can see, it's dropping like crazy, okay? You do expect essentially to see essentially very few quiescent galaxies in the early universe. And in particular, in our survey, we would expect to see about 10 to the minus 3 of these galaxies. So essentially, there would have been impossible to detect this one. So if I put this, our spectroscopically confirmed case at redshift 7 here, this would be already of the order of 3 orders of magnitude higher than the density expected by these simulations. We have actually a few additional photometric candidates, and these would put the tension even higher by more than 3 orders of magnitude. So I think this probably there is some mechanism that it could be the first black hole seed accreting and ejecting gas, the first supernovae that is not incorporated in the subgrid physics of these models that is responsible for this high fraction of quenched galaxies at high redshift. And with this, I'm concluding. And just this is the list of take-home points for at least for what I could talk about. So we have hit the redshift frontiers up to redshift of 13, and large fraction of these galaxies have extremely strong emission lines, which has implications for their photometric properties. These lines are characterized by extremely high gas excitation, probably associated with partly the very dense, dense radiation field. The galaxies, these galaxies are typically metal poor, but with a large dispersion. And we have found a population of accreting low mass black holes whose contribution to the overall light in these early epochs has to be assessed, but could potentially contribute to this very high luminosity function that we see at high redshift, with a very high black hole to galaxy mass ratio, much higher than seen locally, typically hosted in low metallicity galaxies and driving these mild outflows. Very interesting, we have found this population of massive quiescent galaxies at redshift 3, which actually have properties which don't show any sign of dynamical harassment, implying that the quenching of star formation has been gentle, and that the dynamical and the morphological transformation must have happened later on. And they essentially all of them, what we, as far as I can say, host an AGN which may be associated with not only quenching but also maintenance of quenching. And really puzzling is finding this population of quenched galaxies beyond redshift 7, which is I think was unexpected. And so the question now for people, simulators in this room and theoreticians, is to explain what is the mechanism responsible for quenching them now. And there are many other things that I couldn't discuss, other results, and more to come in the coming months. But of course, so stay tuned. And I would just thank you for listening. Thank you.
Thank you for Roberto for coming and telling us, and also for sharing quite a few unpublished results and giving us this flavor of the excitement, which I certainly think has been transported into the room. And I'm sure there will be several questions. So first of all,
you should take some of the students. Okay. These are fantastic results. So I think this is really a discovery machine. I have maybe a comment and a question. So I think on the last point on the quenching, if you look at semi-analytic models that try to model really low mass objects and build them star by star, I think we see this quenching quite a bit in these objects. So I was not aware that this is an interesting prediction to make.
I had the same comment, but I should actually expand my high redshift plots to show more visible. This is indeed. But I've seen indeed, I think the only one that hopefully there will be more publication focusing on this low mass, high redshift regime. But the ones that I saw, I think explored this more in detail are the summation by Severino, where they actually do this, show this stochasticity in the star formation, but it's a sort of they never reach total quiescence. I mean, in this case, we are realizing the galaxy is temporarily, at least temporarily, completely shut down. No hint of any star formation. It doesn't mean that they will not restart and they are created at some point, but it's interesting that they reach essentially the zero level. I mean, I think the upper limits we have on star formation rate is 10 to the minus something other.
So I agree, this is seen in Daniel Severino's first light models, but I was more referring to semi-analytic models that can recover the same thing. But my actual question is, and you kind of have avoided this topic. You showed luminosity functions as function of redshift, but what about the star formation rate that you estimate? Do you think all the points we see so far that have been published are severely overestimated because of the effects you have shown?
Okay.
Overestimating mass and redshift?
There is a plot that by Richard Bowens, which actually I didn't put it. Well, I in translating I removed the spare slides, but for the moment, our estimation of the star formation rate at high redshifts is a lower limit because we can only locate the galaxy for which we have confirmed the spectroscopic redshift, okay? And for the moment, our lower limits are consistent in principle, are lower than the previous estimations, but since our lower limits are consistent with the higher one. There is a work by our colleague with the NICAM team which tend to make them the luminosity function more complete, and they start to be consistent with some of this work, not the most extreme luminosity function that have been published, which are, I think, a factor of 10 nearly higher. So we're consistent with the more, how to say, milder luminosity function, although these are still somehow higher than what expected by many simulations. Okay, so we tend to see everything to be confirmed with because that's we are cautious in publishing before we are super sure about the results. We tend to be consistent with these to say mildly elevated star formation rates, but not with this extremes one. And the questions that I want to assess is how much of this excess of star formation that we are seeing is actually due to contribution by AGNs, because we are actually seeing an increasing number of AGNs which contribute to the light. And I'm not sure how much this is contaminated, what we think is the UV light associated with, which we think is star formation, but actually is black hole accretion. So that's what I would like to explore more in detail in the coming months. Yeah.
Thanks. You showed us some fantastic looking spectra. And I was wondering, when you were talking about the mild ionized outflows, if any of the spectra allow us to maybe see the sodium absorption lines to give any constraints on what these outflows might look like in the neutral phase. Yeah,
generally, no, it's very faint, but we do see sodium in some cases. This is, no, it's not shown here. But for instance, this galaxy here does have, unfortunately, is not in this spectrum, does also show evidence of ionized outflows and also blue shifted sodium, and so indicating that there is a cold, say, a neutral phase of the outflow. But assessing the mass is more difficult because it depends on the covering factor and so on. But yes, there are a few cases where we do detect that. Yeah.
Okay, thank you.
Back to the slow mass quenched galaxies at Z around 7. Assuming that they are quenched really by a sudden starburst that drove out all the gas, then there will be a very, very quiet period for those. No quasars, no supernovae, but it's early in the universe, so there's a lot of primordial gas around. Does it mean that they could collect again and get revived as a kind of later a spiral galaxy, and the original one, the quenched one, is then the bulge?
Could very well be. And if I look at some of these simulations, again, also 10G50, I think they expect a lot of stochasticity where the galaxy can go to very low level. I don't know if to these low levels, but then rejuvenate by accretion. Yeah.
Hi, Roberto. A very exciting talk. Thank you very much for sharing the results. I was very excited by all these spectra that you're showing, these galaxies about redshift 7, even 10. So I was wondering if they have the quality to see the IgM damping wing on them.
Yeah.
And if so, if you can estimate how neutral is the universe around them.
Yeah, that's another revolution of, from my perspective, of Webb NIRSPec, that for the first time now you have quality of the spectrum, the continuum of galaxies to do the damping wings on galaxies. So essentially do the mapping on the close line of sight even of the damping wings, something that until recently was doable only with quasars. But yes, it's a hint is already in the paper by Emma Curtis-Lake, where we attempt that, but that's a redshift 10, where essentially you expect everything neutral. But the idea is now to explore the intermediate redshift across serialization to do the evolution of the damping wings. Yeah.
Then let us thank Roberto again for this fascinating insight, and good luck over the next months and years. Thank you.